everyone. Welcome to my talk. My name is Saad Sajid Hashmi, and today I'll be talking about longitudinal compliance analysis of Android apps with privacy policies. The team members for this work are myself, Nazar Waheed, Gioacchino Tangari, Muhammad Ikram, and Stephen Smith. Firstly, I'll be talking about the motivation behind this work. Now, in this paper, we have tried to answer this question, whether the compliance of mobile apps and in specific Android apps with their privacy policies is getting better or worse over time. There has been some existing work in the literature about contemporary apps not being compliant with the stated disclosures in the privacy policies, but their longitudinal trend over time has not been covered. So in this paper, we aim to determine if the non-compliant behavior has changed with time or not. So for our work, we have collected historical Android apps from 2008 to 16 for 268 different apps, and having collected 5,240 versions or unique APKs. And for the privacy policies, we leverage the Internet Archive Wayback Machine, and we have captured or downloaded 3,151 unique privacy policies or privacy policies obtained at different timestamps. This is a broad overview of our work. So firstly, I'll be talking about the setup for privacy policy analysis. Now, once we have downloaded the privacy policy segment, we scrape the body tag, and we discard unnecessary content that is nested in other tags such as script and style. And existing work has shown that if the policy is divided into multiple paragraphs or segments, the prediction of PII disclosures is improved. And so we convert the privacy policies into segments or paragraphs. And we then extract vectors by taking the union of TF-IDF vector and manual handcrafted features. We treat the problem of identifying PII disclosures in privacy policy statements as a classification problem. We subdivide the classification tasks to identify three things: the PII type, such as email and location and so on, performed or not performed, meaning whether the statement is saying that the PII is being disclosed or not disclosed, and then to which party it is being disclosed or not disclosed. For our work, then, we require 32 classifiers in total. So there are 28 for each unique PII types, one each for performed and not performed, and one each for the parties. We utilize the OVR classification strategy with the linear support vector classifiers. Now, we also tested our approach with the logistic regression and the multinomial naive Bayes, but because the testing accuracy on the app 350 corpus for these two approaches was not as great as with linear support vector classifiers. So for the unseen privacy policies, we predict them with the linear support vector classification. Now, what's app 350? It's a corpus of 350 annotated policies that have been annotated by legal experts and law students. Now, a couple of classification examples. So if there is a statement, your email will be shared with our partners, the PII type is the email, so contact email address. And the statement is saying that the email will be shared. So performed classifier will return positive value. And then here it is our partners. So the third party classifier will return a positive value. Another example, your phone number will not be collected by us. So here the PII type is contact phone number. The statement says not be collected. So that means then not performed. Classifier will return a positive value. And by us, so it's first party that is being talked about here. So the first party classifier will return a positive value. Now from 3,151 privacy policies, we were able to obtain 143,783 policy paragraphs or segments. And among these policy segments, the number of segments that returned a positive value for all the three categories, that is a PII type, performed, not performed, and first third parties, their number is 19,371. And we term these segments as valid segments. And throughout our work, we have only analyzed these valid segments. Now the breakdown of valid segments by performed, not performed, and parties is as shown here. So here, a vast majority of these valid segments have a positive value for the performed classifier, which is performed only plus both. That comes out as 18,882. And then these number of segments here are divided by the values for the parties classifier. So here you have 13,698 policy segments returning positive value for the first party classifier only, and 2,240 segments returning positive value for the third party classifier only, and 2,944 segments returning positive value for both first party and third party classifiers. Now let's have a look at our static analysis. So once we download the APK, we then perform static analysis. The first step is we decompile the APK using APK tool. And from there, we extract API calls from small-d format. Then we extract app permissions from the Android manifest file. We then map API calls to PII types. We identify that a leak has happened or has occurred in the APK if both the relevant API calls and the permissions required for that PII type exist. If the API call is there, but the required permission is not there, so we don't identify that as a leak of that PII type. And based on who made the API calls, we distinguish them into system calls, first party calls, and third party calls. Now, overview of our dynamic analysis. So after we have downloaded the APK, we then also conducted dynamic analysis. And for the dynamic analysis, we use a tool called Recon that is based on the decision tree C4.5 classifier. And that is used to predict whether the traffic generated by the app is leaking PII or not. And how is it able to do that? For its feature set, it uses concatenation of the text of the URI, the referrer, post data text, and all other HTTP headers in the flow. And to automate interaction with the apps, we use the Android's UI app exerciser monkey that generates pseudo-random user events such as swipes, clicks, touches. And to capture the app-generated traffic, we use a man-in-the-middle proxy. So once we have leaks identified through the static analysis and leaks identified through the dynamic analysis, we take union of those leaks, and we then compare them with the disclosures of PIIs in the privacy policy statements. And if there is a leak that is found in either the static or dynamic analysis, but not found in the privacy policy statement, then we say that a violation has occurred. So let's have a look at the results of privacy policy analysis. What we notice is that newer versions of privacy policies, they a large number of them disclose less number of PII compared to their preceding version. So here, the dashed lines represent the decrease in the number of practices disclosed by the privacy policy, and the dotted lines show an increase in the number of practices disclosed by privacy policy compared to their preceding version. And we can see that the dashed lines are always higher than the dotted lines, meaning that privacy policies each year, they are disclosing less number of PIIs compared to their preceding versions. Or we can also say that privacy policies are shrinking with time. Then regarding the sensitive API calls, we noticed that more than 3/4 of these API calls were made by third parties. And this is the breakdown of API calls to access different PIIs. And regarding leaks and violations by APKs, we observe that they are on the rise compared to 2012, where you had 40% of the APKs that were leaking at most 2 PIIs. This percentage had dropped down to 35% in 2016. Similarly, in violations, we observed that in 2012, more than 70% of APKs had at most 2 violations, whereas this percentage had dropped down to nearly 40% of APKs in 2016 having at most 2 violations. And among these violations, what we noticed was that the average leaks that cause violations have been on the rise, especially to third parties. So this is the summary of leaks and violations. And if you look at the last column or the rightmost column, that's the average leaks per APK to third parties that violate privacy policy. And what you can observe is that since 2010, it has been steadily increasing. That is the number of leaks per APK to third parties that violate privacy policy has been on the rise steadily since 2010, sorry. So from 0.32 in 2010, it had increased to 1.94 in 2016. And we observed that newer versions of apps, they continue to leak more PII that violate privacy policy. So here you can see that the dotted lines, they represent the increase in violations compared to the preceding versions, and dashed lines represent decrease in violations compared to the preceding versions. So we can here see that the dotted lines, they always remain higher than the dashed lines, meaning that newer versions of apps, they leak more PII that cause or that violate privacy policy compared to their preceding versions. So this is across different versions of the same app. And we conclude by identifying the causes that increase the violations. So firstly, privacy policy has shrunk. That can be one of the reasons why there is an increase in violations. The behavior of app has changed. That is, it's leaking more PII, or both 1 and 2. And what we observe is that it is indeed both 1 and 2, meaning that the privacy policy has shrunk, that it's disclosing less number of PIIs, and also the APKs are leaking more PII, especially to third parties. And in our future work, we aim to study the compliance trend in recent years, and especially look at the impact of GDPR on the compliance. And also, since app developers are not expert in the domain of privacy policy and compliance, we aim to determine whether they have been using third-party privacy policy generators. And if so, these privacy policy generators are non-compliant. For more details, please refer to our paper. And if you have any queries, you may reach me on the email address mentioned here. Thank you all for your attention.